Good morning, good afternoon, good evening. Welcome to my YouTube channel, TESI, a channel for theoretical experimental scientific investigation. Today we're going to talk about the linear Hall effect sensor or ratiometric sensor. So these are very important because they allow you to calculate the magnetic field in a specific region in the space and also to perform some test analysis or to establish, for example, if a magnet, where is the magnet? Where is the magnet? The magnet is, okay, I'm going to take this one. Right here, if this is the North Pole or the South Pole. So the agenda today is the introduction, fundamentals, very simple equations, benchmark setups, Arduino and a sensor, and some experiments. Now, a magnetic field sensor, which is linear, is characterized by a behavior that is linear. It's simple, but there are some other sensors that are not linear. They are called digital, and they work according to the concept of switch on off, from lower state to the upper state, from 0 volt to at a certain value, for example 3, 4 or 5. It depends the characteristic of the manufacturer that he gave to the sensor. So in this 2 point we can see one sensor that when you show the south pole on a specific phase of the sensor, it gives you a higher voltage, while you show the north pole of the magnet is going to give you the minimum value of the voltage. So this instead is the behavior of a digital sensor. As I said before, it switches from the lower value to the upper value, and obviously it requires a different electrical connections. Now, how the Hall effect sensor works? Substantially, it's a matter of interaction between electrical charges and magnetic field that approaches to it. You use two equations, the Lorentz force equation and the Gauss force equation. The first one relates the force that electrical charge is subjected by the magnetic field by using the charging itself, the velocity of the charge, because the electrons moves in an electronic circuit. So, but when you put a magnetic field for the force for the Lorentz force, the trajectory of the charged particle deviates from the nominal one. In the Gauss force, it states that the force is directly proportional to the electrical field by the electrical charge. By combining these two equations, you can carry out the relationship between the voltage and the magnetic field, as you can see here. Now, as I said before, sensor and Arduino 2560 and the sensor DRV5055 that you can directly purchase from Texas Instruments in this website. Then the sensor is characterized by 3 pins. We have the power pin, the ground pin, and the output that has to be injected directly into the pin A0 or any analog pin that you can find here in the Arduino. I built this feature when I locate a sensor in this phase, the lower one, as I recommended by the datasheet. So this one is the side that the sensor will view. Every time I approach with the magnet to this phase, which is this, I can vary the magnetic field. So in this case, I am facing the south pole, so south pole gives a positive voltage and it goes up to this value. Now, I set up some equations. So I took two values far from saturation points. I named it BNVN and BSBS, respectively magnetic field and voltage of the North Pole and magnetic field and voltage of the South Pole. I measured the magnetic field by using a very nice Gauss meter. This is Lapnex MF-30K, and some measurements of the voltage that I took by using a very simple multimeter. You can buy this one very cheap, but this one cost me like almost $300. I set up some equation. The voltage from where I carried out the expression of the magnetic field, as is the slope of this straight line, which intersects the vertical line at the alpha of the power voltage. I established some floating values, floating because there are decimal points, they are non-integer. And I represented in the program the value that I have obtained right here. This expression instead is the analog digital conversion of the voltage, where basically allowed me to calculate the value, the analog value, to implement in this straight line, in these equations. Once we go down, we're gonna make some experiment. So, as I said before, we have substantially the analog pin A0. Arduino has to read the analog value. I put some setups. As I said before, this one has been represented in the previous page. I represented also the floating value of the voltage and the magnetic field, and I start to print. Pay attention that I multiply by 100 the value of the magnetic field, otherwise I cannot see directly in the serial plotter. Remember that the magnetic field that I measure is 29 millitesla, okay, so 0.029. So I should obtain it basically some values, and moreover, an important information is that you have to make sure that you are far from the saturation, as I said before. So don't put the magnet close to the center, otherwise you reach the saturation point and you cannot establish anymore the linear pattern that allows you to convert the voltage in magnetic field. You put, for example, this side on the top of this one, and then you put on the fixture the sensor. I'll show you where the sensor is. I'm gonna put this one here like this. Hopefully it doesn't fall. Oh, wait one moment. All right, give me the camera. I'll show you here. This is basically the way I put it, and as you can see, there is also values they carried out. The value, holy moly, this is falling. Okay, let me see if I can fix the camera. Yes, the value is close to the 29. By moving it, probably I might be able to reach 29. It probably can be reached. Yes, I put just right in the middle, and instead in the serial plotter we have this beautiful behavior. There you go, right here. You see, I move it, and it oscillates. So this is the North Pole. The North Pole is where you have the countersink hole of the magnet. So you approach to the sensor and it goes negative. So, or the minimum voltage value, where the orange is the voltage, the yellow is the magnetic field. So the negative value is going to be this. And there you go. And then we have the North Pole, sorry, the South Pole. I made confusion. All right, as you can see. So very easy. Why is important that basically the calculation of this one? For example, can be important when if you analyze some magnetic interference, or you want to basically understand if there are a problem of electromagnetic compatibility. Well, for that reason you need basically also the value of the frequency. For that reason I will present a video where I extract the value in LabVIEW, and we can make also the FFT analysis. In another video I will show also the so-called MATLAB implementation where they read the value of Arduino that allows you also to plot the data. But for today it's fine. I would like to thank for this video Lab Center, Lab Electronics, that allow me also to use the software Proteus to develop substantially the electronic circuit. This is a very nice software. In the website you can find a lot of resources. Consider that the software is used by Lockheed Martin, Boeing, NASA, and some other company in order to provide a very professional production. I use this one, for example, to make my PCB. As you can see, over there is my CNC machine that I have. Let me see. Hoppla. There you go. Where I used to print also my PC board. Anyway, guys, that's it for today. Thank you so much to connect, and if you like the video, subscribe. If you have any questions, please send me an email. All my contacts are just right there. See ya, guys. Thank you so much.